how are my exams doing? How many questions have you solved or attempted to solve?
I'm not starting till tomorrow.
Well, be careful, guys. Hopefully I haven't tried too hard, right? I mean, the questions are not all easy, right? I would say that there are 3 easy questions, but maybe that's what I think that they're easy. Maybe you would not. I chose 3 questions, and I was rather worried that you would find those questions boring. I gave you 3 boring questions, and I tried to give you some that are not boring. If you and don't worry too much about it, just do your best, and do not cheat on the exam as has happened in the last situation, right? Because then I feel like I'm not teaching you and I get rather upset. And if I get into my moody states, I might play a Russian roulette with you, right? I would just generate a random number and I would just pick the person that will be decimated. Understood? I don't believe you do, but fine. You might think I'm bluffing. I'm pretty, because you might think, okay, he'll be too busy and you will not want to do that. And well, maybe you're right, but you know, if you get me into one of those moods, I will really become bloodthirsty. All right, so I'm rather sad, but I think I will skip the very last question from last section. You know, about the expected value and the terrains and when you should leave to get to your destination. You read it on your own. And let's go into the next topic, continuous random variables, and that was uniform. We want to talk about the simplest type of continuous random variable, the uniform random variable. So uniform is our sense of every point between A and B is equally likely to be selected. Yes, and everybody sees why the density function has to be a horizontal line. Yes, that's very obvious because you see, how can you imagine? You can imagine that it's a discrete random variable. And if it is a discrete random variable, it's like this. So you have this small pillar. It's a small box. It represents essentially the probability of selecting numbers that are A-like, right? If it's very thin, you cannot really tell the difference between A and what's next to it, its neighbor. It's like A plus or minus a billion or something, right? So that's going to be this representation. On the other hand, let's say if I want this X, its representation, if it is to have equal probability, the box representing the probability of picking it is going to be of the same shape. Yes, and so the skyline has to be a horizontal line. You agree? The skyline of those hair-thin skyscrapers is a horizontal line. That's why uniform random variable is like this, as simple as possible. Now, what is the cumulative distribution function? Well, first of all, the density function, before I say cumulative distribution function, density function has to be 1 over the length of the interval AB. Do you agree? Because the area is B minus A multiplied by the height, and that's supposed to equal 1 because the totality of probability is 1. So that makes the altitude C equal to 1 over B minus A. Now, for the cumulative distribution, what's the probability that X is less than or equal to T? It's just the integral from minus infinity to T, which in this case happens to be the integral from A to T, which happens to be T minus A over B minus A. You agree? So the probability that the point X chosen is below some value T is just the length, the distance between T and A divided by the distance between B and A. Yes? So another thing you should right away expect is that probability here is directly related to the length of the interval. So you don't even need to calculate integration most of the time. But this thing is, you can take lots of shortcuts, and you should, right? So that's the way the cumulative distribution function works. Notice that the cumulative distribution is defined over the entire real number line. It's just 0 below A. Then linearly it climbs, you see it's a linear formula, climbs to 1 at B, and then it is always staying at 1. And here is what I just said. The probability, if I is a subinterval of AB, the probability that X is in I happens to be the difference between the cumulative distributions, right, at the endpoints of the interval, which is the same as the length of the interval divided by the length of the total interval AB. You understand? That's a very important point. It's just that means that you can calculate probability by directly looking at the comparison of the interval that you're looking at, or interval of interest, to the total interval over which the distribution is defined. So for instance, suppose that, let's do a quick check and see how fast you can answer this question. So X is uniformly distributed between 0 and 20. What is the probability that X happens to be between 5 and 10? So what's the probability of generating a number between 5 and 10 if we are uniformly generating a number between 0 and 20? Please, as quickly as possible, type in the comments. Well, very good. 5 over 20, don't need to simplify, right? 1/4 is great, but you understand the point is, you see how it's generated. It's 5, it's 10 minus 5, the length of this interval, to the total interval, right? So integration wise, you can see it's, you integrate 1 over 20 from 5 to 10. You all understand why it's 1 over 20. That's because the total distance would be between 0 and 20, and multiply the total distance by the height has to give you 1. So it has to be 1 over the width. And that's 1/4. And probability that X is bigger than 5 is simply 20 minus 5 over 20, which is 3/4. Right? Now here is another question. I'll just very quickly go over it. Suppose that theta is uniformly distributed from 0 to 2 pi. And that means that I want to know what's the probability that sine of theta is less than 1/2. So instead of looking at less than 1/2, I'll say what's the probability that sine of theta is bigger than or equal to 1/2. You can, by the way, be very loose about the 1/2 because probability of every single point is 0. You can always say bigger than 1/2, less than, or, you know, it doesn't matter, right? You can always drop the equal situation since it's not, one number is not going to add probability if the distribution is continuous. So what do we get here? Sine is bigger than 1/2 if theta is between pi over 6 and pi minus pi over 6, or 5 pi over 6. In other words, sine is bigger than 1/2 in the first and second quadrant, right? So it's either it's a 60 degrees or 30 degrees or higher, right? 30 degrees or higher in the first quadrant, or go to the second quadrant to pi and go up 30 degrees or higher, right? So that's the interval. So what do we get? And second. So yeah, so what we then have is just what's this? That means that theta is this distance. We just take 5 pi over 6 minus pi over 6, which is 4 pi over 6, and multiply by the reciprocal of the length of the full interval, 0. Yeah, it's basically by 1 over 2 pi. And then we see that the answer is 2 over 6, or 1/3. And therefore, the other probability, the one we want, is simply 1 minus 1/3, and that's 2/3, right? That it's less than 1/2. Make sense? Hopefully it does, guys. So next example. Next example, trains run every 10 minutes. So they run at 2 o'clock, at 2:10, at 2:20, and so on. And you come to the station uniformly between 2:05 and 2:35. What's the probability that you have to wait under 5 minutes, less than 5 minutes? So the way I solve this question, I just say x plus 5 be the time of arrival. So x plus 5 is when you come, right? So you come, so that would be x is between 0 and 30. I just readjusted it this way. So then your wait less than 5 minutes if you come where x plus 5 is between 5 and 10, or x plus 5 is between 15 and 20, or x plus 5 is between 25 and 30. And obviously there are intervals of the same length. There are intervals of length 5. So we can just take 3. It's the same as 3 times the probability that you come between 5 and 10. And that probability is what? That probability, x plus 5 is distributed uniformly over 30, you agree? So that means that it's 5 divided by 30, and that's and if you multiply it by 3, you get 1/2. That's the probability. Good. I'm not going way too fast. So far, you will follow me, guys. I'm just trying to capture as much as we can before the class is over. It's like you have only a few lectures left. Okay. So now we talk about Bertrand's paradox quickly. And that the idea is just there's something strange that might happen in terms of uniform or equal likelihoods that are somewhat in the continuous case not the same. So let me explain. A chord is randomly drawn on a circle of radius r. What is the probability that the chord is shorter than the length of a side of an inscribed equilateral triangle? So let me show you what an equilateral triangle is. So you have a circle of radius r and an inscribed equilateral triangle. You can just quickly see that that means that all the legs are of the same length. By symmetry, that means that the angle between, you can just draw the triangle and draw inside of it in blue, draw the, I call it the support structure. Like if it's an umbrella, it's the support structure of this umbrella. And you can see that the radii are spread apart at equal angles naturally, right? Because this angle corresponds to directly proportional to this length, right? And therefore this angle has to be also directly proportional to its to the length, and they have to be therefore the same. And I know that this angle is then 2 pi over 3, correct? The angle is 2 pi over 3, and there is this equilateral triangle. I can use the theorem of cosines to figure the length of the chord if I wanted. Good. So what do we do then is how are we going to perform this experiment? So we have this red chord. We're going to drop it, and it's going to fall in a circle. And where it intersects, you see it intersects, let's say in this case. In this case, the intersection is shorter, right? So it's smaller than the length of the chord of the equilateral triangle. Or if it fell here, it would be longer. Now the chord can fall under any angle. So to make this thing simple, here is how I imagine the problem. I imagine that you have a glass table. So you have a regular table on the regular table, you have this drawn triangle. Here it is, right? That's the triangle. And on top of it, you have a rotating glass circle. So what I do is I drop the chord. It can fall maybe like this. And I will just rotate it until it is parallel to this leg. And then I am going to verify whether or not the chord is shorter or longer than the side of the equilateral triangle. So far, good? Stephen, I mean, Nicholas, yes? Good, all right. That's the idea. So then we can ask this question in several ways. So how do we measure this probability? So first, what do we mean by equally likely to fall? Where is it equally likely to fall? Is it equally likely to fall on any length y? Clearly, you see, if I rotate it, I might as well say that the chord falls from 0 to r on y. Do you agree? Because whenever it falls, I can just rotate it. Let's say the chord falls here. I rotate it until it's in this vertical position, and then it is intersecting the y-axis at a right angle. Yes, however it falls, I rotate it and it will intersect the y-axis at the right angle. So let's assume that it's equally likely to fall anywhere on the y-axis, right? So when is it going to be longer? It's going to be shorter if it falls in this region, and it's going to be longer if it falls in this region. Now, how did I ask the question? I said, what is the probability the chord is shorter? So I asked, what's the probability it's shorter? So it has to fall in the later part of the y-axis, farther from 0, right? Now, how much farther from 0? By the theorem of cosines, I know what is this length, right? And what is this length? This length is, it's the same as cosine of pi over 3. Cosine of pi over 3 multiplied by 2. So cosine of pi over 3 times r is this length multiplied by 2 gives you this full length. Yes. So the angle, the angle here is the angle here is going to be pi over 3. And if the angle is smaller than pi over 3, then it's it's over there, right? So you can see clearly that one is the angle, one is this what is the length of this segment? The length of this segment is the same as cosine of pi over 3. And you see, so it's this length here, I'm sorry, the y part is cosine of sine over 3. The length of the chord is sine of pi over 3 multiplied by 2. Yes. So if in that situation, y has to be bigger than or equal to r divided by 2. And if you calculate the probability, we assume uniform distribution over y. That means we take r minus r over 2 and divide by r. That's r over 2 by r, and that's 1/2. The probability is then 1/2 that it will fall in the later part. It just happens to be exactly 1/2 here, in the y-axis. You understand, guys? I'm not too loose in my explanation today. Confirm if you followed what I said and how I reasoned. Or you want me to re-explain?
Seems reasonable to me, but I'd love to see it worked out on paper, step by step.
Yeah, you can. I'm trying to hurry up. That's why I'm a bit, loose about it. You can read this thing and try at home. That's the best way you can understand. If you know it at home, you try to reproduce the argument without looking into my notes, and then look into my notes if you're stuck. Yes. But the idea is, you just have to very clearly imagine how you perform the experiment. What do you mean to drop the chord? And what do you mean to say that the chord is equally likely to fall? Where is it equally likely to fall? So I can make two assumptions, right? I can make the assumption that the chord is equally likely to fall on any part of the positive y-axis from 0 to r. Now, why only on the positive y-axis? Obviously, I can drop the chord diagonally. It can fall on the circle in any which way. That's where I imagine that I have this that it's on a rotating glass platform. I imagine that there is this pillar in the middle, and it's suspended from the ground. On the ground, I have drawn this equilateral triangle, and this pillar is on this pivot axis. I can rotate the glass table. So then when the chord falls, I rotate the chord falls on the glass, and I rotate it until it's perpendicular to the y-axis, right? And I imagine that if I do this rotation this way, and then I will see that the chord is equally likely to be anywhere on the y-axis from y equals 0 to y equal to r. Make sense? It is the diameter if it's at 0, and it is the tangent if it is at r. So if that's the case, the probability this chord is shorter than the leg of the equilateral triangle happens to be 1/2. And how did I reason 1/2? It's just this length here is 1/2. It's r over 2. This length is r over 2. It's half of it. Now, why is it r over 2? Because the angle here is 2 pi, which means half of this angle. You see, half of this angle is, you see, here it is, right? Up to this point. Half of this angle is pi over 3. Cosine of pi over 3 is 1/2. So this side is 1/2, and this side is 1/2. You with me? Yes, that's how I reason 1/2. Now, the other thing I can imagine is perhaps the chord is falling in such a way that every angle is equally likely, right? So I still rotate the table, but now I'm assuming every angle is equally likely. But how many angles do we have, right? So if I describe it by equal likelihood of angles, that means if the angle is 0, then I am a tangent line. If the angle is pi, right? If this angle is pi, then I am the diameter. So maybe I imagine that the chord is equally likely to fall on an angle between 0 and pi. Yes. And if that's the case, look at it. This angle is 2 pi over 3, right? This angle is 2 pi over 3. So that means that my angle has to be smaller than 2 pi over 3, right? 2 pi over 3 or smaller, that's 2/3. Do you see that? 2 pi over 3, that's 2/3 of the full angle motion, because my full angle is from 0 to pi. Now here I can go from 0 to 2 pi over 3. And 2 pi over 3 is 2/3 of a pi. And that means the probability then is 2/3 rather than 1/2. Do you see? So assuming that the angle is random makes the y-axis not random. And assuming that the y-axis is equally random or equally likely, then it makes the angle not equally likely. Is this surprising to you or not? I mean, it's called Bertrand's paradox. You understood what happened, right? So we had, we said there was some ambiguity, right? We said the chord is equally likely to fall anywhere, but then we see that, well, what do you mean by equally likely? If the angle between 0 and pi is equally likely, any angle is equally likely, then the distance from the origin is not equally likely. Some distances are favored, right? 2/3, you see, I mean, this 2/3, it means that it's the upper part of the y-axis is going to be favored if the angle is equally likely. You see, it's probability it will fall anywhere from 0 to the chord, right? It's 2/3, so that means that it will prefer this segment. Yes. Well, I don't know. It doesn't surprise me too much because, again, imagine you are in a big room, right, guys? And the person is equally likely to be anywhere in the room. That obviously makes, and you're watching the person from a corner, right? Not all the angles are equally likely because if a person is very distant, let's imagine you have several football fields, right? So if the person in the other, halfway farther than you, the angle is kind of not changing as much, maybe, right? The angle changes more when the object is close to you. So it's not so surprising to me, at least. You understand what I mean, right? So if something is equally likely to be in a big field, then it's equally likely to be close to you, maybe, and far away from you, right? And if it's equally likely to be very close to you and very far away from you, it cannot be that the angle is equally likely, because if you look at faraway places, the angles for faraway places are kind of similar, and the angles for near places are much more diverse. That's kind of how I understand it. And where did you disappear? There you are. Good. Now let's calculate the expected value. Now the expected value of a uniformly distributed random variable is the integral from ab of x 1 over b minus a dx. And a very simple calculation gives you that the expected value is just the average. That's natural, right? So the average is the expected value. Very, very predictable, I think, because if everything is equally likely, the balance point is right in the middle between a and b. And variance, we can calculate variance by calculating the expected value of x squared minus the expected value squared. Same formulas work. Now we can see that when you carry the calculation and simplify, you get b minus a squared over 12. So you can carry this calculation, or you can use parameter adjustment. You can calculate the expected value for the simplest distribution for where the it's a square where base is 1 and height is 1, and you can just readjust by parameters. Would you like me to show you how to do that, or are you satisfied with this? Yes, show you how to do the parameters. Okay, I will try. So what you can do is, and sometimes it's better, you can take the function, let's say it's equal to 1 if x belongs to the interval 0, 1 and 0 otherwise, right? This is the standard distribution. It's basically you generate a number between 0 and 1, yes? And we will try to understand all the others by looking at what happens when you standardize. This is the standard uniform distribution, right? If we can say it so, right? So then what is the expected value? The expected value of this standard uniform distribution is the integral from 0 to 1 of x dx. And what do you get? Obviously, you get 1/2. Yes? Naturally, you get 1/2. Now, because, you know, it's the integration here, right? Now, what about the expected value squared? That's just the integral from 0 to 1 of x squared dx. And what do you get? You get 1/3. You agree? It's just integral. It's 1/3. Right? And so the variance of x from this information is 1/3 minus 1/2 squared. Good. And what do you get? You get 4 minus 3 divided by 12. Yes, which is 1/12. It's a bit easier than with having a and b. So you see that variance of that variable is 1/12. Yes. Now, how do I manufacture a uniform? So suppose that I have now y, and y is uniform over the interval, I don't know, a, b, right? So how can I make y out of x? So y is the variable. So first of all, it has to have length b minus a, right? So it's b minus a times x, right? I made it by b minus a larger, and I need to shift it to a. You agree? So it's b minus x, b minus a times x plus a. You see that? I'm basically constructing from, I'm constructing the general uniform variable out of the standard, right? And then what is going to be the expected value of this thing, right? So expected value of y, expected value of y is it's linear, right? So it's going to be b minus b minus a. It's going to be b minus a times the expected value of x plus a. Yes. And what do you get? You get that this is we know the expected value of x is 1/2, so you get b minus a divided by 2 plus a, and that gives you b plus a over 2 average, right? It's going to give you b plus a divided by 2. Good. Now, what about variance? Variance is you see variance of y is equal to variance of b minus a x plus a. Now, variance doesn't care about shift. You know, if you shift it by a, it doesn't affect variance. You understand it, right? It's easy to see that. It's just because it's y minus the expected value. So it's, you know, it's going to cancel out the a there. So it ends up being the same as the variance of b minus ax. It's the same as variance of b minus ax, which is, you can factor out the constant by squaring it. It's b minus a squared variance x. And we calculated variance x before, it's 1 over 12. So it's b minus a squared over 12. And this calculation is faster and easier than the one I showed you in my notes. Do you see that? So it pays a lot to realize that you just really have to understand one variable and deform it to make others from it, right? So that's how you can do it. You see this calculation, you can carry it out, but look at it, I simplify squares. If you actually decide to do it, you can try doing one calculation, another, and time yourself. And you will see this one is faster. I mean, not this one, the one I showed you on the white, but this one is pretty slow. Okay, now here is an interesting result, very interesting. And it's called the universality of uniform random variables. So from a theoretical point of view, you don't need to understand any other continuous distribution if you understood the uniform distribution. You can simulate any other distribution from it. Okay, and here is how. So suppose that I want to simulate a random variable x with a continuous probability density function f of x, and of course, if I have little f of x, I can have the cumulative distribution capital F of x. Okay, so that's enough to describe any continuous random variable is to know the distribution function, right? This distribution function that tells you what's the probability that x is less than a particular value. Right? If I know this, I know everything about this random variable. And suppose I have the uniform random variable available to me, right? How am I going to generate the variable x? And this is what it tells me to do. It tells me just take the inverse function of this f. I'm assuming that this capital F is increasing, by the way, right? So I'm assuming it's always increasing in some interval. So if I take the inverse, if I take the inverse of u, I will be able to use u to generate x. Okay, and similarly, if I have any other distribution, I will be able to generate the uniform distribution by doing this. Okay, let me try to explain how the first is going to work. Okay, so let's we have the uniform u, and it means just a number between 0 and 1 is randomly generated. The standard uniform distribution number between 0 and 1 is generated. I will define y to be equal to the inverse of u. In other words, what I do is whatever number I get, and I'll take the inverse of it. I'll see what I have, right? This function capital F is defined, as you know, from -infinity to infinity. So what is the probability that y is less than a? It's going to be the cumulative distribution. Yes. And so what's the density of y? We'll take the derivative of this expression. That's the same as the derivative of u being less than or equal to capital Fa, which is the integral from 0 to capital F of a du. And when I take the derivative, what do I get? I mean, I just get the derivative of this capital F, which is little fx. So it has the density function. I didn't actually have to go this way. It's enough to say we have the same cumulative distribution. It's also fine. You see what just happened? In other words, this process is going to give me. It's going to simulate the random variable x. You see, the reason it simulates the random variable x is basically you go through the probability, right? So the cumulative distribution is giving you probabilities. Now, from those probabilities, I can go back to the value of the random variable, so to speak. When I do that, that's what I essentially produce, right? So when I take inverse image, if it's a continuous variable, I kind of go back to the variable that was generated. Yes. The other way around is this. You see, so if X is a distribution that I have available to me, I can apply I can plug it into its cumulative distribution and call it U. Now, what's the probability that U is less than A? It's just the same as FU of A, right? And the derivative, the density function is what? The density function is the derivative of FU of A, which is the derivative of this expression. Now, and what's the derivative of this expression? This expression is the derivative of X less than or equal to the inverse at A. I just apply inverses on both sides. And what is this? This is the derivative of, this is the definition of cumulative distribution at X, where you plug in the inverse function into it. They cancel each other, and I have the derivative is just ends up being equal to 1. So what this tells you is that you can, if you have any other continuous random variable, you can generate the uniform distribution from it. Yes, so it's enough to know one continuous distribution to figure out every single other continuous distribution. Any questions or too many questions to ask? All right. So think about it, right? See if it's intuitive to you. Yes. Think about it really and see if you can make it intuitive. If you would have thought of this argument, and that's the biggest important thing, guys. You see, you can know that something is true, but do you really understand it? You see, is it artificial? It's like, you see, you can have a heart, or you can have a lung, or you can have a kidney, but is it your kidney, or is it implanted and you constantly have to take immunosuppressants to keep it there, right? That's the same thing in mathematics, right? You see, there are many things that you might know, but it's not natural. And if it's natural, then it's yours now, right? You have to make it part of your organism, part of your thoughts. Okay, so when here I gave you this dry kind of presentation, but really think about it. If you want in office, we can talk about it more. You need a clear side. You have to think, why is it obvious? So, how can I make it obvious to my mind? And if you can, then you understood it. Good? Not just a calculation that you remember. So next we talk about the normal distribution. So normal distributions are continuous functions. We begin with the standard normal. Standard normal looks like this. So it's e to the minus z squared over 2, where z is between minus infinity and infinity, and it's multiplied by 1 over root 2 pi. Yes? Now, why is the 1 over root 2 pi there? It's a corrective factor, because the integral of e to the minus z squared over 2 from minus infinity to infinity has to be 1, right? And what it happens to be is root of 2 pi. That's why we divide by it. See this part, we divide by it so that we don't get root of 2 pi, but we get a 1. How do we do that? Well, we can use calculus, calc 3 in particular, which you remember well, correct? You know it very well, and it's intuitive to you. At least integration is, yes. So I will show you why the change of variables goes here. It's a good way to review it quickly. Okay, so what we can do is we can define I to be the integral from minus infinity to infinity e to the minus z squared over 2 dz. That's I, right? Which is the same thing if I change z to x or z to y. It's just called a dummy variable. It doesn't matter. It's a symbol. It's not really doing anything beyond that. But this gives us a very nice multiplication. I can say that I squared is the product of the expression involving x with the expression involving y, which I can then write as the double integral. Guys, Don't be scared. Why can I do that? Well, really, what is this? This is just summation multiplied by summation. And what does this represent? This represents the, what you call it, foiling, I think, right? I forget which way is foiling and which is factor. Anything is foiling, that's right? So you interlace the summation. So that means for every x, for every y, you have this combination. So it's just like having two parentheses, one addition, one parenthesis involving lots of additions multiplied by another parenthesis with lots of additions. And this is the combined FOIL expression. Yes. And this is the double integral, dx dy, which means for, in this case, I followed it in this way. I said, for every y, I have this summation, right? You see what it is? It's like, it's very, very similar, but that's what I mean by seeing it, right? It's like, I have each term of x here, right? So for each term of this has lots of y's in the summation, right? Something y1, y2, y3. For each yk, I have the full sum of all the x's. That's what this is saying. You see it? It's just it's exactly like in elementary school when you expanded parentheses, and when I have this double integral, I'm just saying each single term of y has the full summation in the x. Should I write it on a separate page, or do you follow my explanation? You see it, right? You see in your mind. It's like a huge addition in one parenthesis, huge sequence of additions in the next parenthesis, and this is just I take the second parenthesis and I bring it to every term. That's what this means, right? Very simple. But now we can avoid doing it this way. You see, because we are adding those terms up, but I just look at the region and I realize, I can describe what this thing is. What is this, guys? This is, I call it when I taught Calc 3 years ago. I decided to stop, by the way. You know why? Because too many people, not too many. I had one semester where the people were so scared of the way I taught it that somebody complained, and I decided I don't want to bother with them. Right? So they turned my my efforts. You know, I thought I shoved so much material into them that they were not all happy, and I did it my way. Yeah, so I decided, let me just talk to probability, or to people that care about those things more. So, what is this? This is a baking pan. Right, so you know my example was always Aunt Jemima. So you go and you have this, you buy a baking pan, maybe for Thanksgiving actually, right? You have a baking pan and you want to make a cake. So what sort of cake are you making here? Can anybody describe me? What is this cake? I mean, I don't care about the cake, but what pan have you got yourself? You understand? That's the question, right? So what pan did, you know, those metal foil, whatever they are called, things that I only know in theory, you know, I never cook anything. So you understand, but that's why I'm a theoretical cook. What are those things? Double layer. I mean, you know, you go into a supermarket, right? You go into a supermarket and you select your pan, right? So maybe you want to have a frying pan that looks like this for your kids. I don't know, right? Baking pan, you know, like you make cookies, right? For your, I don't know what you have there, right? To make cookies for. So you have this baking pan, you have this baking pan in the supermarket, you have this type of baking pan, you have this type of baking pan, right? So cookie cutter type of baking pans, right? So I'm asking you, what is this baking pan in this particular situation, right? So you see the integrals tell you what the baking pan is. Tell me what it is. What do you think? Well, it's a bit tricky to say what it is in this case, but there might be more than one answer that is right. You need to go to the supermarkets, guys, I think, right? You haven't looked at pans in a long time, I think, right? Nobody sends you to the grocery store anymore. So in the first part here, it looks to me like like a square, like an infinite square. It's essentially a square that is expanding you know, in all directions to infinity. Why? Because if it were bounded, it would be, let's say, minus r to r, where r is large, and minus r to r dx dy, or whatever other arrangement you would like, right? What is that? What is the dy minus r to r? It means what? It means that when you baked your cake, you're going to slice it, right? So what is this saying? This is saying that this is saying what? For every y, for this y that you select, for this y, you have the cake is sliced this way, right? So for every y, you have, this is the slice. The slice for x is between minus r and r. So the intervals are all the same. Do you see? How do I know it's not a triangle and not anything else, right? Right? How do I know that? It's because do you see what I'm saying? Yes. Yes. Some people, I guess, liked my lecture so much that they decide to join. I see. That's nice. That's nice. I like to have such very viral influence on people. All right, maybe some more of you will be learning Russian after you're done with it. Try to remember me. So you understand that this is invariant, same thing, correct? And if I select a different y, it will be same thing, right? That's how I know this baking pan is a square. Now, if I had a different Thanksgiving baking pan, right, a triangle, as maybe Barry suggested, let's consider this this type of triangle. Okay, this is the baking pan. What's going to be the difference when you bake something and describe it? So, for instance, let me describe it in terms of, so let's say this is, let's say from 0, and this is to r, and then the y is from 0 all the way to r as well, let's say, right? So what is happening here? So this line is obviously y equals x, you agree? So this line then is y equals x. And if the line is y equals x, then if I slice it horizontally, so for a fixed y, I want to make this horizontal slice, right? What's going to be that horizontal slice? It's going to be different in length. It's going to react to the y, you agree? So it's going to be what? It's going to be from y all the way to r, right? So the integral is then going to be from y to r dx for a given y, right? And then y is how many slices we make? We add up over the slices from 0 to r. So 0 to r dy, right? That's the appearance of a triangular you know, baking pan, as I call it. Yes, in the integral you can realize how somebody was cooking their Thanksgiving meal, correct? In theory, only in theory. What? But because you know, so you understand, you have to train yourself at least in some basic shapes to look at the integral and realize what was you know, it's like what was somebody cooking, how they were cooking it. Yes. Okay. And now, do you see that, guys? So if it's between minus infinity and infinity, you see it's like minus r to r minus r to r. That means we have a square baking pan. The only thing is it's so large, it's so generous, it's a Thanksgiving miracle. It is infinitely wide and infinitely long. Yes, but an infinite square is not very different from an infinite circle, at least so it appears. Yes, I can think of it as an infinite circle, correct? So that's what I'm going to do now. I'm going to describe this pan as an infinite circle, because that's going to make it easier to integrate the cake. So it's so if it's an infinite circle, I can describe the radius as from 0 to infinity, and the circumference as the angle, sorry, as from 0 to 2 pi. Yes. And then I have to make a correction, guys. Do you see what's the correction is? I am adding up areas, right? I'm basically slicing the same cake, and I just need to find the volume of the cake, correct? So here is how I find it when I do Riemann sums. If I do Riemann sums and I do that for a square, if I do Riemann sums for a square, I can imagine that the cake is sliced into many quadratic sectors. Like this, right? And I just add up over the volumes of those sectors, yes? Now, if I am going to slice it in the inside of a circle, right? The slices that I'm going to perform are going to be protractor-like slices. They're going to look like this. It doesn't matter, guys. You're still going to eat the full cake, correct? It doesn't matter. The volume is still going to be the same, right? But I need to describe those different shapes. What are those different shapes? Look at it. I need to figure out what is this area, right? So this area here is very simple, right? It's dx, dy, right? What about this one? So you see what happens here is this segment, it's difference in r, so it's dr, right? What is the length of this segment? Well, the angle is stable. This angle corresponds to d theta, right? The angle is d theta, but d theta is not changing. You agree that if you move farther, it should be bigger. But so what is the actual region? It's a circular sector. So the actual region is r d theta. So it's the r d theta. Do you understand why we change the coordinates? So we have what? So this dot here is f dx dy. So f represents the what do you call it? The height. It's in this case a cube or a three-dimensional shape, right? I just showed you the frying pan, but the f represents the crust. The crust is not uniform. It's different here. The crust is different from here. But I can imagine the frying pan, each sector is kind of uniform. If you make it small enough, it's kind of uniform. You understand? Slice it with very, very thin slices and many circles around it, kind of uniform. So, but what's the uniformity here? It's like if I want to understand the volume of this shape, it's going to be f multiplied by r d theta multiplied by dr, because this shape has area r d theta dr. That's your change of variables there. You remember now? And that's wonderful. So what do we get? So here is the change of variables, right? X squared plus y squared happens to be r squared. Isn't it nice? So we have r squared over 2 with a minus, and here we have the corrections. And then from there, it's easy to integrate. You just integrate it and you get 2 pi. So I squared is 2 pi, which means I is root of 2 pi. How beautiful. Right? And then this Russian letter, anybody knows what it means? That's the Russian fe sound. It's the Russian letter fe. Right. So yes. Well, so this is the that's how you denote the. Yes. Yes, and that's how you denote the standard normal distribution. Yes. Yes, indeed. Yes, as somebody remarked, that's a filthy f. Right. Indeed. So so what we have here is it's from minus infinity to z. This is the lowercase letter. That's the standard normal distribution, and this is the cumulative distribution that we have. It's not easy to calculate those integrals. You need to use approximations. Yes. That you have computers for, but we can argue about certain symmetries. We see that, for instance, that this function, it has a z squared, right? You see it has a z squared, which means that if I replace z by minus z, there is not going to be any effect, right? So there is symmetry of the probability density function, and of course you have symmetry of tails. You see, because clearly. If you integrate, because of the symmetry of shape, if you integrate from below minus z or above z, that represents the distribution above z, they have to be the same. Yes, that's clear intuitively. And here you have an argument supplied. I will skip it as I think it's pretty simple to see it, right? You have the bell-shaped curve. It's symmetric shape. So if you calculate the left tail, it's the same as calculating the corresponding right tail, correct? So z and minus z that's another thing. Z and minus z are both normal standard distributions. Minus z just reverse everything, right? It's like what we do in today's time. We usually say what's good is bad, what's bad is good. So that's a minus z type of reversal. Distribution wise, it doesn't change anything. Okay, this is a proof that that if you replace by minus z, you still get the same variable. So minus z less than or equal to z is the same as z bigger than or equal to minus z, which is the same as 1 minus phi of minus z. Right, to calculate it above is this above minus z is the same as 1 minus calculating the tail below minus z. And what is that? That's by definition, by a previous symmetric argument, the same as phi of z. So that means it's normally distributed. And now let's try to calculate the expected value of the normal. So the expected value is multiplied by z, and it's very simple because now it's an odd function. If you multiply it by z, it's an odd function. So what do you get? The integral is 0. Yes? And now we can calculate the expected value of z squared. The expected value of z squared is just, you have a z squared there, and then your favorite, guys, you have the integration by parts. The integration by parts tells you that when you carry it out, you get 1. Can you imagine what happens if I ask you to integrate it, to integrate z cubed, z to the 4th, or find a general formula for the nth moment? There is actually a very easy way to do that, but not through here. There is something that you need to learn. It's called moment generating functions. And an interesting part of the extra credit question that you had in the previous exam, the last question on the extra credit exam, if you remember, the people dividing into pairs, has a lot to do with this normal distribution, right? So in fact, if you actually were deriving the expected value, the z to the nth power, you would be dealing with that extra credit problem. You would realize it's a combinatorial problem. Isn't it interesting? So the variance is, as you can see, equal to 1. Yes, those are calculations that you can all carry out, or you probably know from previous classes. Maybe you've taken psychology or almost majored in it. Yes. So now let's try to understand how to figure out, without doing too much calculations, the other normal distribution. So another normal distribution with with mean mu and standard deviation sigma can be defined by mu plus sigma times z. In other words, sigma will kind of stretch. You know what sigma does? It's stretching the variable, right? And mu is shifting it. So you have the distribution. You can stretch it and move it around. So what do we get? So this would be this is going to be called normal distribution. Now, what's the expected value of normal distribution? Well, it's mu plus sigma expected value of z, which is obviously mu. So you can see this new distribution has average mu. And what about the variance? The variance is x minus mu squared. So if I subtract mu, I just have the expected value of sigma z squared, which is a factor sigma squared, and I have expected value of z squared, which is 1. So I can see that by doing it, I just changed the variance to be sigma squared and the average to be the expected value to be mu. Yes, very simple. And you can usually you can go back and forth. If I have a normal distribution, I can rebuild the standard normal by subtracting its average and dividing by sigma. That's just reversing the calculation from here. That's why you do it. See, that's something you probably learned in previous statistics classes if you ever had them. Of course, you're much better off if you never had the other classes, right? Because they are usually filling your head with lots of incorrect information. Good. So the cumulative distribution at x is the Russian distribution at x minus mu over sigma. Good. And when you take the derivative, you can see what it will be, right? What is the density function? If you take the derivative of this capital function, it's really the derivative of this standard normal distribution at x minus mu sigma. And when you take this distribution, it's what? It's going to be the standard normal density function evaluated at x minus mu over sigma multiplied by 1 over sigma, right? If I multiply it by 1 over sigma, I have 1 over root 2 pi time in here as a sigma. And here I, instead of x squared over 2, I have x minus mu squared divided by sigma squared. Do you see that? Carry those calculations and be sure that you understand. You're following what I'm saying so far, guys? Not losing you? Not too fast? Yes, maybe a lot, but you know. Make sure, guys, again, I cannot stress enough. I mean, I don't want you to do the exam at the last moment. Look at each question. You should try to aim at 1 or 2 questions per day. Better 2 than 1, but maybe the questions are difficult. Look, if you are stuck at one of them, go to others. All right, so here is this next theorem. So it happens that we have the 68, 95, 99.7% rule. And that tells you that 68% of the values x fall within 1 standard deviation away from you. Within 2 standard deviations, 95% fallen, and within 3 standard deviations, 99.7. So you can see that well, you know, you've known it's the same for heights, right? So for instance, if people's heights are normally distributed, then it's unlikely that somebody is going to be 3 standard deviations away from the average, right? It's very unlikely, right? It's and already 68% are within 1 standard deviation of the average. All right, so let's consider a small example. Let x be normal with mean -1 and variance 4. What is the probability that x is less than 3 exactly in terms of phi and approximately? Yes, exactly, right? I never remember anything. I forget those rules very quickly. So how do we solve it? We can say that probability that x is less than 3, it's the same as probability that x is between -3 and 3, which is, I want to introduce the mean and standard deviation. So we know the variance is 4, so the standard deviation is root of 4, which is 2. So what do? I subtract -1, that is adding 1, and divide by 2. Do you see what I do? And what do I get? I get the standard distribution, the standard normal. It's between -1 and 2. So the exact value is phi of 2 minus phi of -1. Right? And what is that? This I can also write if I don't like to use negative numbers. And the reason I don't like to use negative numbers is historical. In other words, right now you have computers, it doesn't matter much. You can just quickly look at the answer, right? In your machine. But you had tables and you would have only positive values because the distribution is symmetric. To make the table easier to read, you have positive values, right? So let me show you how the table looks. I think I have it somewhere here. Here it is. That's the table. Do you see? So you have it's only for the standard normal that you have the table. So you always have to convert to the standard normal. Now the computer will do it automatically for you, right? And here you have what you see only the cumulative distribution. So you would have to use the cumulative distribution to figure out the particular probability you care about, right? So you can see z is between 0 and 3, only positive, and so I cannot look into the table z equal to -1, right? I do not know what's the integral to -1. That's why I use the conversions. You see, so if I have phi equal to -1, it means probability that something is less than -1. It's the same as the probability that something is greater than something is greater than 1, right? Probability that something is greater than 1, which is 1 minus the probability that something is less than 1. So you see how I get it, right? And then it becomes f of 2 plus f of 1. Phi of 2 plus phi of 1 minus 1, right? That's this formula. That's the exact solution. And if I look into the table, I can then look, okay, what is phi of 2? Phi of 2, this is phi of 2. What is phi of, I subtract, I add to it phi of 1. Phi of 1, I add this number, and I subtract 1. And I have my approximation in the table. But if I don't look into the table and I remember the 68, 95, 99.7 rule, then I can do as follows, right? So what do we have here? I have here the distribution is between z is between -1 and 2. So z between -1 and 1, that's 1 standard deviation away, right? So it's the same as 1 standard deviation away, that is 68%, and between 1 and 2. Right. So what is that? So how do I calculate this last part? It's the same as taking the distribution from -2 to 2, subtracting the distribution from 1 to 1, and dividing by 2. You agree? Because if z is between -2 and 2, that's 2 standard deviations away. And I subtract from in the middle, from 2 standard deviations away, I subtract 1 standard deviation away, and then I have the 2 wings, right? And then the 2 wings are of the same length, so I divide it by 2. Yes, so that's what I do here. So you see, it's this probability plus what I mean here is divided by 2. It's the probability that you're within 2 standard deviations minus probability that you are within 1 standard deviation, and divided by 2 because you only want one of the wings. You only want z between 1 and 2, and not z between -2 and 1. Agreed? And that allows you to get this number without the table. Very good, guys. My God, we finished almost the normal distribution. That's the way to go. Yeah, somebody is suggesting that I should let you go for Thanksgiving, but I think no, we're celebrating it together. Right. In fact, I think since it's Thanksgiving, we are going to stay here longer, maybe an hour longer. Just because somebody wanted to leave early, that's exactly what will happen. Believe me, guys, if you had to write the papers I do, you would prefer to do probability. You would enjoy it so much. You know, it's like imagine sitting on nails, right, for many months or years, and then somebody tells you you can now sit on sharp stones. You know, you would be so happy. It would be the best. All right, good. Let's continue. So folded normal. So y is the absolute value of z. Yes, you are my distraction, but I enjoy it anyhow. I mean, you know, I do actual exams, right, for fun. You know, so you understand what happens to you, right? So expected value of y Yes, for fun. I'm not interested in becoming an actuary in the list, right? I think about crow questions that I can ask other people, and that gives me the joy. Right? So the expected value of y, if y is the absolute value of z, that's what we're going to try to calculate. Okay, that's the absolute value of z multiplied by by the standard normal cumulative standard normal density function. So because of the absolute value, obviously we can simplify and say it's twice the integral from 0 to infinity. Yes. And then how can we calculate this thing? Well, this is not too bad. We can actually, there is a z there, we can use a u substitution. We can integrate it. Here is the integral, and simplified, it's root of 2 over pi, voila. Then we want to calculate the variance. The variance, it's what? It's y squared equal to z squared. You see, because look at it, if I square this thing, it's really the same as the expected value of z squared, and I know it to be right away 1. We already calculated it, except we need to, this time the variance of y is not just the expected value of z squared, it's the expected value of y squared minus the expected value of y squared, the square of this number. So it's 1 minus 2 over pi. Yes, and then finally we need to figure out the density. I mean, so we want to figure out the cumulative distribution function first. The probability that y is less than y is the probability that absolute value of z is less than or equal to y, which is the same as the probability that z is between minus y and y, which is this cumulative distribution at y minus cumulative distribution at minus y, which I can simplify as 2 times phi y minus 1. Do you see? Because this I can replace by 1 minus phi of y. That's right, because of symmetry. That's what we have here. And now I can take the derivative, and the derivative is twice the cumulative twice the density function at y. I hope, despite my malapropisms, you're able to understand and follow, right? Because I sometimes think carelessly, whatever I say doesn't matter. Just sound coming out from me, and you're just looking at the clock. I know. I have been there in things ironically known as extremal length seminars. It's a mathematical thing. It's called extremal length, and those seminars, they're like 3 hours long, and the people there want to make them longer for some reason. They ask lots of questions. All right. And then, of course, we have this thing. If x is a normal random variable with parameters mu equal to 3 and sigma squared equal to 9, we want to estimate those probabilities. We can use tables. This I will leave to your enjoyment. You understand how to use the table, or do you want me to explain it? You don't, right? So this is just using the table, which of course is, honestly, for us, it's not so important. You can use a computer, but if you are taking the actuarial exams, they will give you a table. They will not allow you to use a computer. You understand? So you still need to know it. Right?
The value we look up in the table is what you are using in your phi function, correct?
Yes, that's what you use in the phi function. Phi, here is the picture to remind you, phi is the cumulative distribution, right? So this table only tells you the probability of getting values less than z, right? So the probability of getting values below, let's say, 2.4 standard deviation. So I look at 2, and then I go to, here's 0.04 or something like that, right? And I do my best to kind of match it, you see, to find the right type of position, right? This is 2.04, it goes by those digits, right? You can see here I can go by 10th digits, and here I go by 100th digits, and I just kind of find the intersection, and that's, let's say, this is, let's say, 1.441, it's here. I look at this value. Yes, so you see that they're only positive values. You will have to convert. That's the annoying thing. But of course, you just take any app, any computer, you don't even need to convert. I mean, you have an app that will just, you tell it what's the mean and what's the standard deviation, and right away it tells you, and what's the values of X that you're interested in, right away it tells you the probability, right? So it's very convenient. This is a sort of anachronism. Also, unfortunately, necessary because people cheat, because they if they have a computer, they can do a lot of other things other than just look information in the table. Too many things. It's pretty scary. All right, but it's not. It's the table, I presume, is not useful anymore. Just like logarithmic tables, nobody does it anymore. All right, so what more? The lesson is done for today, guys, but maybe you have questions for exam 2 that you work very hard on, correct? Do you have any questions for me?
I was looking at question 1. I haven't really put in any much, major effort. So to get started on this, I should make the protocol for the 5 cats.
You can make a protocol or not. The point of the protocol is it has to be in your head always, right? If there is no protocol in your head, then you might be confused. But we learned many things now. We have what do we have? We have Bayesian inference, right? So we have all sorts of things. They're all related, and you can use that to figure the situation. Just what you have to figure out, it's what happened here, right? So what you actually witnessed and what's the question that you try to understand. So obviously this question seems to be using Bayesian inference. That's just a hint if you need it.
Right.
You see why? Because there are a lot of if, right? I mean, you have the evidence and you can consider under which circumstances the evidence is more likely. Is the evidence more likely? First, obviously, there's how likely is the thing to make the evidence very likely, and then under the situation that you have this, if the father cat is Siamese, then that means perhaps more likely that you have more kittens that are Siamese, correct? But maybe it's not likely that the father is Siamese because there are no Siamese cats around, not enough of them, you see? So that's the things that you have to take into consideration, right?
So for this, we should work out like a prior and a posterior.
Yeah, exactly, okay. Right? You should work out prior and posterior, but be careful, And then anything else, guys? Here is another question. This one is, I'm really interested in what you would answer for this question. Very interested. Not an easy question, I think. But maybe I'm wrong. Maybe an easy question. I told you that some of those questions are easy, some of them are not easy. Extra credit is, I don't know how easy it is, right? But this is a gift for you for Hanukkah if you celebrate. Okay. And if you are learning German, feel free to submit the exam in German. It's up to you, of course. Yes? You can write in Russian if you want it, or in Hebrew if you want to. It's up to you. You can write in Italian. I would be interested to see it, but probably with Italian, I will need extra help. But I would need to have extra notation, but I would be interested to see Italian. Yes, good. Okay. What is it? All right, guys. So Yes, happy holidays, guys. Enjoy it. Have a good one. If you have anything else you want, you let me know. Yes, happy Thanksgiving, Stephen. Take care, guys. Okay.